This is the second set of notes in our homeostasis and transport unit, this one on osmosis and cells. These notes will be doing in class. I'm just posting these here if you want them as a refresher or if you happen to miss the discussion in class. Here we go with our second set of video notes, this one on diffusion and osmosis in cells. You probably got a handout in class that looks similar to what you see down here, so you can just attach that to your notes and make things a little bit easier. If you don't have that handout, then yes, you should draw this in the next 3 slides in your notes as well. So to begin this discussion, we have to come up with a little bit of terminology. Talk about solvents and solutes. A solvent is simply a solution that does the dissolving, right? So it dissolves things, versus the solute is a thing that gets dissolved, the stuff that gets dissolved. So in our diagrams here, we've got a couple things going on. We've got water molecules, right? Lots of water molecules. Those are solvents. They do the dissolving. Think dissolving stuff in your Kool-Aid. And the solute are these little balls here. These are things that are dissolved inside the water. And then, of course, we have our cell over here with its nucleus and its cell membrane, which is selectively permeable. Okay, so if you recall what we already talked about when we talked about water, and we talked about our water and our cell membrane a little bit earlier, last set of notes, water can move through the cell membrane whenever it wants to. So it can come in, it can go out, it can do whatever it wants, right? Solutes, on the other hand, cannot. These guys are too big, so it can't just go in or out of the cell whenever it wants to. And we're going to see what happens to our cells as we put them in different solutions of water and what happens as we do that. So in this first situation here, we have our same cell and we have our water molecules all throughout here, our water molecules, and we have equal amounts of water inside and outside the cell. Now remember, this water can go inside the cell if it wants to, it can leave the cell if it wants to. The water's free to go wherever it wants. Okay. Now we're also going to add to our mix here is we're going to add some solutes. So here's some solute, some solute, some solute, some stuff dissolved in that water outside the cell. And there's going to be some stuff inside the cell too. All right, some solute. So yeah, you should be drawing this just like I am. But notice we have a lot more solute outside the cell. Okay? And so really what the story is here is the cell wants to maintain equilibrium. It wants there to be equal level of stuff inside and outside. So let's pretend that our solute here, our solvent is salt. That's easy to think about, right? So it's salt. So right now the water outside the cell is very, very salty, right? And the water inside the cell is not very salty. And this cell wants to make the waters the same saltiness on both sides. So one solution would be, oh hey, why don't we just let some salt into our cell and then we could balance it out that way, right? But can that happen? No, right? This salt can't go into the cell at all. The cell membrane is selectively permeable and it can't get through. Okay, so, well then, the only other thing we could do, the only other thing the cell could do is try to dilute the saltiness on the other side. So it can take some of its water molecules and send them out, okay, and try to dilute that salt. And that would, in effect, add more water to the outside of the cell, dilute that salt, and try to get it towards the same level of saltiness. Now, if water is leaving here, what's going to happen to this cell? All right, this cell is losing all of its water. That's what makes up the cell. The cell is actually going to shrink. So what we have here is a hypertonic solution. Right? So we have a solution in which there is more solute in the solution out here than there is in the cell. So if a cell is placed in a hypertonic solution, the cell will shrink. So the cell loses water and shrinks when it gets placed in a hypertonic solution. Now let's look at the opposite situation. In this case, we have a hypotonic solution. So now there's going to be more solute inside the cell than outside the cell. Hypo means like less or low. Think of hyper as like hyperactive means more activity, so hypertonic has more stuff. Hypo, like hypothermia, means there's less stuff. So in this case we have a hypotonic, so there's less solute in the solution. And we have the same thing. The cell wants to make everything the same level of saltiness. All right, so there's more salt inside the cell. Can the cell say, hey, salt, get out? No, the salt can't fit through. So then the cell can do something else, or the only other thing it can do is bring some water in to try to dilute that salt. So kind of the same principle as last time, except in reverse. So now there's going to be water entering the cell. So in this case, this cell is going to get much, much larger. So I'll say that again. The cell size increases because water has entered the cell if you place it in a hypotonic solution. And finally, as you can probably guess, we have our last situation, which is called isotonic, where things are the same. So we have, we'll say, 3 solute molecules out here, 3 solutes inside, so there's equal level of saltiness, and so now the cell's pretty much happy. Again, the salt can't enter or leave, no big deal. If the water decides that it wants to leave the cell, it can leave, but as soon as it leaves, equilibrium is lost, it's no longer isotonic, and another guy will enter to replace it. So again, like that seesaw that wants to stay balanced. So as soon as one leaves, one enters. This is happening all the time, just in equal amounts. So everybody's happy and the cell is going to have its normal size. So an isotonic solution is a solution that has the same amount of solute as the cell, so water will enter and exit the cell in equal amounts and the cell size will stay the same. When we apply these same principles to a plant cell, we talk about a term called turgor pressure. And turgor pressure is just the pressure that is exerted on the inside of the cell wall. So if we take a cell and put it in a hypotonic solution, then it is going to gain water. And so in this case, it's like a water balloon that's really full. Is there a lot of pressure pushing out in that water balloon? Yeah. Is it ready to pop? Yeah. So this cell has high turgor pressure. Isotonic would be, again, in and out in equal amounts. This would just be, I guess, the medium or the normal amount of turgor pressure. And then if you put a cell in a hypertonic solution, water is going to leave the cell, and this is where you're going to have low turgor pressure. This is the situation where your garden or your flowers or your potted plants, you haven't watered them as much, and they all start to droop because they have low turgor pressure. Your vacuole, you can see the vacuole here. The vacuole is pretty much empty. There's not a lot of support, so your plants are droopy or wilted, or this is your celery that is all floppy and not nice and crisp. All right, with that, that ends the second set of notes.